We think we see it all, right? The whole rainbow of colors. But it's really just a tiny, tiny slice of this vast electromagnetic spectrum.
Yeah, the visible light we're used to is really just the tip of the iceberg.
Right. And today we're diving into a region you might not be as familiar with, but it's gaining a lot of attention. The terahertz range. Ever walk through one of those airport security scanners?
Mm-hmm.
That's terahertz in action. And in medical imaging, well, it's showing huge promise there, too.
Absolutely. But there's a catch. Terahertz waves. They're tricky to control. Think of it like trying to sculpt something incredibly intricate, but with very clumsy tools.
Not exactly a recipe for precision.
Exactly.
Yeah.
And one of the biggest challenges has been manipulating their polarization, the direction these waves vibrate.
Polarization. Got it.
Up until now, it's meant relying on all sorts of external components. Big, bulky pieces of equipment.
Not exactly ideal if we're trying to build smaller, more integrated technologies.
Right.
So that's where this new research from Beihang University in China comes in. These researchers have come up with a totally innovative way to control the polarization of terahertz waves. And get this, they're doing it right at the source. No more bulky add-ons. It's all built in.
It's a game changer. We're talking about going from a whole rack of equipment to something that could potentially fit on a microchip.
A microchip. That's incredible. And that's what we're going to unpack today. We'll break down how this new technology works and why it's so exciting for things like faster wireless communication, more detailed medical imaging, even pushing the boundaries of quantum research. All that tailored for you. So let's start with the basics. What exactly are terahertz waves? Where do they fit into the electromagnetic spectrum?
They sit right between microwaves, the ones that power our Wi-Fi and our ovens, and infrared light, which we feel is heat.
So kind of the middle child, maybe a little overlooked, but with some special talent.
Exactly. They have some unique properties that make them so fascinating.
Okay, let's hear it.
They can pass through materials that visible light can't, and they do it without causing harm. Think clothes, paper, even some plastics.
That explains the security scanners.
Exactly. But what's even more intriguing is their sensitivity to biological molecules.
Biological molecules, as in living things.
Yeah. You see, different molecules, they absorb terahertz radiation at specific frequencies. So each one has its own kind of spectral fingerprint. It's like a unique identifier.
That sounds incredibly useful, like for detecting subtle changes in tissues or maybe identifying different chemicals.
Right.
But why is controlling polarization, that direction the waves are vibrating, why is that so important?
It's like having an extra knob to fine-tune how these waves interact with matter.
Ah, okay.
With polarization control, we can make them more sensitive or transmit information more efficiently.
Okay, I'm starting to see the potential here. So how were we controlling polarization before this new invention?
We were using external optical components, things like wave plates.
Wave plates, what are those?
Imagine them like special filters for light. They alter the polarization state of a wave as it passes through. Or we'd use metamaterials.
More jargon.
Sorry. Basically, they're engineered surfaces that have properties we don't find in nature. They can bend light in really interesting ways.
So it was all about manipulating the waves after they were already generated.
Yeah.
And what was wrong with that approach? Was it just bulky?
Well, there were a few problems. These components, they only worked well for a limited range of frequencies.
That's a problem.
They also caused energy loss, so the system was less efficient overall.
And then there's the size issue.
Right. You can't exactly build a handheld terahertz scanner if you need a huge separate box just to control the polarization.
It's like trying to design a smartphone with a giant clunky antenna.
Yeah, a bit like that.
So this new breakthrough is all about solving those problems, making things smaller, more efficient, more integrated.
Exactly. This research, it was published in Advanced Photonics March 20th, 2025, and it introduces a whole new approach.
Okay, tell us more.
It's about integrating the polarization control right into the emitter, the part that generates the terahertz waves in the first place. No more external components.
So they've basically redesigned the emitter itself.
Yeah, it's pretty ingenious. They've incorporated this microscopic stripe pattern into the emitter's structure.
A stripe pattern.
Wow.
Interesting. So walk us through how this works. What's the emitter made of?
They're using thin films of different materials. Tungsten, cobalt, iron, boron, platinum.
Okay. A mouthful.
And they shine ultra-fast laser pulses onto this layered structure.
Laser pulses. Sounds powerful.
They are. And when these pulses hit the material, they generate something called a spin current.
Spin current. What in the world is that?
Think of it like an electrical current. But instead of just carrying an electrical charge, The electrons are also carrying a quantum mechanical property called spin. It's like they're spinning as they flow.
Okay. Not gonna lie, that's a little over my head.
Fair enough. But the important thing is this spin current then gets converted into a regular electrical current.
Okay, so laser in, spin current, then electrical current.
Got it. And here's where the stripe pattern comes in. It influences how that electrical charge is distributed within the emitter.
Oh, okay.
And that redistribution creates a built-in electric field.
A built-in electric field.
Right. And this electric field, this is the key. It directly affects the terahertz waves as they're being emitted.
Right.
It controls their amplitude and their phase.
They're what and what?
Sorry. Think of amplitude as the strength of the wave.
Got it.
And phase, well, that's a bit trickier. It's about the timing of the wave's oscillations, where it is in its cycle.
Okay.
But the bottom line is, by carefully designing those stripes, they can control the polarization of the waves right as they're born.
Wow. So the stripes are like a built-in polarization filter.
Exactly.
That's pretty cool. So what kind of control are we talking about? Can they switch between different types of polarization?
Absolutely. And that's what makes this so flexible. Just by rotating the emitter, they can switch between linear polarization, elliptical polarization, even circular polarization.
Circular polarization. What's special about that one?
Well, for certain applications, it's super valuable. Think of sensing molecules that are mirror images of each other.
Okay.
Circularly polarized light interacts differently with each of those mirror images. And this device, it achieved a very high quality of circular polarization, greater than 0.85 ellipticity, and across a broad range of frequencies.
Okay, I have to admit, ellipticity, I'm lost.
Sorry. It's a measure of how perfect the circular polarization is. And 0.85 is very close to a perfect circle. It means the signal is strong and pure, which is crucial for applications like sensing those mirror image molecules.
Got it. So this is a big step forward in terms of control and precision.
Absolutely.
Now, the research mentions they tested 7 different emitter designs. What were they looking for there?
They were experimenting with different stripe aspect ratios, basically the ratio of the stripe's length to its width.
Okay. And what did they find?
A direct correlation. Larger aspect ratios created stronger built-in electric fields, which led to even greater control over the polarization.
So changing the shape of the stripes directly changes the polarization.
Exactly. And by adjusting the orientation of the stripes, they could even switch between left-handed and right-handed circular polarization on demand.
So a total control built right in. This sounds like a huge leap forward.
It is. No more bulky external optics. It opens the door to compact, powerful, and integrated terahertz systems.
Okay, enough with the technical details. Let's talk applications. How could this actually change things in the real world?
Well, think about wireless communication. This level of polarization control could enable something called polarization multiplexing.
Multiplex.
It means sending multiple data streams on the same frequency. But using different polarization so they don't interfere with each other, it could effectively double our data rates.
Wow, so faster internet, faster downloads.
Exactly. All without needing more bandwidth.
I think people will be pretty happy about that. What about in medicine? Could this technology be used for medical imaging?
Absolutely. Terahertz waves are sensitive to the tiny differences between healthy and diseased tissue.
Yeah.
And with this new control, we could get much clearer, more accurate images. It could be a game changer for early diagnosis.
Imagine detecting cancer cells before they even form a tumor. That would be incredible.
Exactly. And beyond those applications, this technology could have a huge impact on fundamental research too.
Like where?
In quantum optics, for instance. This precise control over terahertz waves could lead to more sensitive measurements, allowing us to explore quantum phenomena in ways we never could before.
So we're talking potential breakthroughs in fundamental science.
Exactly.
So it's fast internet, it's better medical imaging, it's unlocking new scientific discoveries. That's quite a list.
And one of the most exciting things is the potential for miniaturization. This spintronic emitter, it's compact and efficient. It could easily be integrated onto a chip.
Like a computer chip.
Yeah. Imagine having all the components for generating and controlling terahertz waves all on one tiny chip. That would make the technology so much more accessible and affordable.
So instead of huge, expensive lab equipment, we could have terahertz tech in everyday devices.
That's the ultimate goal.
Pretty amazing. So where do we go from here? What are the next steps for this technology?
Well, the researchers are already working on refining the emitter's frequency control.
Ah, so even more precise tuning of the terahertz waves.
Exactly. That could open up even more possibilities, new applications we haven't even thought of yet.
It really feels like we're on the cusp of a terahertz revolution.
It does, doesn't it?
So let's recap. What's the key takeaway for our listeners today?
A team in China has developed a revolutionary new spintronic device that allows us to control the polarization of terahertz waves with incredible precision. And they're doing it right at the source, no external components needed.
And this isn't just a cool scientific feat. This technology could change the world. We're talking faster internet, earlier disease detection, and advancements in fundamental science. All thanks to this tiny but powerful device. It really makes you wonder, doesn't it? We've unlocked this new ability to manipulate terahertz waves. Who knows what amazing applications we'll discover next?
That's the beauty of science. There's always more to explore.
Always. Thanks for joining us today, and until next time, keep exploring the unseen world around us.